Welcome! In this tutorial, we'll learn how to analyze heat loss through a plane wall using Abaqus. Our objective is to determine the rate of heat transfer through the wall and compare the finite element results with the analytical solution based on Fourier's law of heat conduction. We begin by creating a three-dimensional wall model. The wall has a height of 3 meters, a width of 5 meters, and a thickness of 0.3 meters. Next, we define the thermal material properties. The wall is assigned a thermal conductivity of 0.9 watts per meter Kelvin, which determines how easily heat flows through the material. After defining the material, we create a homogeneous solid section and assign it to the entire wall. The next step is to assemble the model by creating an instance of the wall in the assembly module. We then create a steady-state heat transfer analysis step. Since we are interested in the final temperature distribution after the system reaches equilibrium, a steady-state analysis is appropriate. Now we apply the thermal boundary conditions. A temperature of 16 degrees Celsius is prescribed on the inner surface of the wall, while the opposite surface is maintained at 2 degrees Celsius. This temperature difference creates a thermal gradient, causing heat to flow from the warmer side toward the colder side. After applying the boundary conditions, we generate the finite element mesh. A suitable mesh density is selected to accurately capture the temperature distribution throughout the wall. With the model complete, we create the analysis job, submit it, and wait for the simulation to finish. Once the analysis is complete, we move to the visualization module to examine the results. The temperature contour clearly shows the heat flowing through the thickness of the wall. Because the material is homogeneous and the boundary conditions are uniform, the temperature varies almost linearly from the hot surface to the cold surface. Finally, we calculate the heat loss through the wall. According to Fourier's law, the heat transfer rate is given by the thermal conductivity multiplied by the wall area and the temperature difference, divided by the wall thickness. Substituting the problem data into this equation gives a heat loss of approximately 630 watts. The finite element results obtained from Abaqus closely match this analytical solution, confirming the accuracy of the numerical model. This example demonstrates how finite element analysis can be used to solve steady-state heat conduction problems and verify classical heat transfer solutions. Thank you for watching. If you found this tutorial helpful, please consider liking the video and subscribing for more tutorials on Abaqus, finite element analysis, and engineering simulations.